Imagine you are building an AI documentation assistant for a massive software project. You want it to answer questions about how the code works, where specific functions are defined, and how different modules interact. For years, the industry standard solution has been a system called Retrieval-Augmented Generation. You might know it by the acronym RAG. It works by breaking your documentation into small pieces, turning them into mathematical vectors, and storing them in a database. When a user asks a question, the system searches that database for the most similar pieces and feeds them to the language model. It sounds logical, but in practice, it often feels like asking a librarian to find a book by describing its cover color rather than its title. The problem is that semantic search is inherently fuzzy. It relies on probability, not precision. When you have thousands of files, the retrieval rate drops. The system might grab a chunk of text that is tangentially related, but not actually the answer you need. This leads to hallucinations where the AI confidently invents facts because the retrieved context was incomplete. To fix this, engineers often have to manually intervene, tweaking prompts or rechunking the data, which is a slow and expensive process. We decided to challenge this fundamental approach. We asked if we really need a search engine to find information that already exists in a structured format. What if we treated the documentation not as a pool of vectors to be searched, but as a virtual file system? This is the core of the Agentic File System Abstraction. Instead of a black box vector database, the AI agent is given direct access to a Unix-inspired interface. It can list directories, read files, and navigate paths just like a developer would in a terminal. The knowledge base becomes a governed infrastructure where context is managed through file operations rather than opaque retrieval mechanisms. This shift changes the role of the engineer from a prompt tuner to a curator of the file structure. To understand why this matters, we need to look at the technical benchmarks. We ran a series of stress tests comparing the traditional RAG pipeline against this virtual file system approach on large codebases. The first metric we measured was inference latency. In a standard RAG setup, there is a significant delay between the user prompt and the final answer. This is because the system must first query the vector database, calculate similarity scores, rank the results, and then assemble the context before the language model can even begin to generate a response. In our tests, this retrieval step added an average of 200 milliseconds to every single query. In contrast, the virtual file system approach eliminates the search step entirely. The agent simply issues a read command to the path. The latency dropped to nearly zero, limited only by the speed of the file system itself. The second metric was token costs. This is often the hidden expense in AI applications. When RAG retrieves context, it often brings in irrelevant information. If the search returns 3 chunks of text but only one contains the answer, you are still paying for all 3 chunks to be processed by the model. Over thousands of queries, this waste adds up significantly. With the virtual file system, the agent navigates to the specific file containing the answer. It reads only what is necessary. In our benchmarking, the token usage per query dropped by approximately 40%. This is because the agent does not need to be prompted to ignore irrelevant context. It is given a precise path and reads the file directly. The third and perhaps most critical metric is cache invalidation complexity. Imagine you update a documentation file. In a RAG system, that update is invisible to the AI until you reprocess the entire dataset. You have to rechunk the text, regenerate the vectors, and update the database. This is a heavy computational task that often requires downtime or complex background jobs. If you update a file in the virtual file system approach, the change is immediate. The agent reads the file at the moment of the query. There is no stale data to flush. There is no need to re-embed the entire knowledge base. This makes the system far more responsive to real-time changes in documentation. Consider the scenario of a large codebase with thousands of interconnected modules. An AI using RAG might struggle to cross-reference multiple documents because the search is limited to individual chunks. It might find the definition of a function, but miss the file where that function is called. The virtual file system allows the agent to perform complex reasoning tasks. It can read a file, see a reference to another file, navigate to that file, and read it. It verifies file paths and establishes connections between documents. This reduces hallucinations because the agent is not guessing based on similarity scores. It is navigating a known structure. This architectural shift also simplifies the tooling stack. You no longer need to maintain a separate vector database or an embedding model just for context retrieval. The agent interacts directly with the storage layer. This results in faster inference and lower operational costs. It unifies context engineering, meaning the way you organize your files directly dictates how the AI understands your project. It shifts the burden of context quality from the retrieval algorithm to the file structure itself. However, this is not without its challenges. Managing a virtual file system requires a different mindset. You cannot simply dump unstructured text into a folder and expect the agent to figure it out. The files must be organized logically, much like a well-maintained codebase. The agent needs to understand the directory structure to find the right information. This means the initial setup requires more discipline from the engineering team. But once that structure is in place, the reliability gains are substantial. The system becomes more traceable and accountable. You can see exactly which file the agent read to generate an answer, which is a significant improvement over the opaque nature of vector search. In our stress tests on large codebases, the difference was stark. The RAG system struggled with context windows that were too narrow to cover the necessary dependencies, while the virtual file system agent scaled gracefully by following the links between files. The token costs remained stable regardless of the codebase size, whereas the RAG system saw costs spike as the retrieval noise increased. This suggests that for documentation assistance dealing with complex, interconnected information, the virtual file system approach offers a more sustainable path forward. It moves us away from the transient nature of search results and toward a persistent, governed infrastructure for context. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.